introduce our second speaker, Dag Aksnes, who's going to talk to us about some surprising and not surprising effects of putting mesopelagic fishes into a model of the biological carbon pump. So, Dag, over to you.
Thank you. Let's see. Okay, can you see the slide?
Yep, perfect.
Okay.
Thank you.
Let's start. So the title, surprising and non-surprising. Actually, this talk is based mainly on the paper down here that was published in August this autumn with several quarters. That has, of course, been part of this. But I have chosen for this presentation to pick topics that are mainly about the surprising parts, not so much about the non-surprising. So first I will give some of the characteristics of the model we use, and also the Red Sea, which is the locations for the baseline simulation that we have established. Then some of the results, which gives how much fishes contribute to the BCP according to the simulations. And then the more surprising things, which are about a role of diatoms actually connected to the mesopelagic fishes here, and the food web cascades involved in this nutrient trap that we call it. And finally, I will have also some remarks about ecosystem closure terms, which is a very important thing in all kinds of ecosystem models. Okay, here is just showing the Red Sea acoustic scattering layers, which shows very pronounced steel vertical migration of 3 species of mesopelagic fishes. So all the fishes actually migrate, and they spend about half the day in deep water and half the day up in epipelagic. Okay. The model is the kernel of the model, which is just a time resolved model, which has been used in enclosure experiments, experimental experiments since over the last 2 decades. The kernel of the model is this blue box, in this blue frame here. And it's based on the model of Tingstad, which stems back actually to the microloop paper, also noted in the previous lecture, back in the 1980s, which Tingstad also was part of that paper, the microloop paper. In the present study, we have put this time resolved model into a water column, representing here the Red Sea, from the surface to the 700 meter. And then we have attached fishes eating on the mesozooplankton. And you also included the detritus divided into 3 groups: suspended, slow, and fast sinking. And all these state variables, except the fish, is expressed according to a partial differential equation, which is solved in time and depth, so we get the depth profiles. And essentially we have the biological processes, which are mainly from this model of Tingstad. We have the mixing, of course, because the water column has some mixing. And we also have sinking of the variables, which leads to gravity flux. The mixing part leads to the diffusive flux. And the active flux is, of course, by fish migration. And the fish migration is forced, which means that it is driven by the observations. So we don't model the migration dynamically. It's actually a forcing of the model. But the fish abundance is not forced. That's is computed from the model. The Red Sea is highly density stratified, at least in the part where in part of the season that we consider, which is in the summer autumn. In that sense, it's similar to the subtropical gyres, but one exception is that the mesopelagic water is extremely warm, about 20 degrees, and it's hypoxic, so oxygen concentration is less than 1 milliliter. This is the oxygen. And the temperature is here about 20 degrees all the way. The water clarity is relatively high, and there is a deep chlorophyll maximum, like here. The euphotic depth is around 80 meters. The zooplankton apparently lack DVM, so it's same distribution day and night, while the fishes has pronounced deal vertical migration, as I said. The model, we run it with constant forcing, and constant forcing here means water column mixing, which is this turbulent diffusivity term, and sunlight, which is kept constant, and top down, the model is driven by fish mortality and the fish vertical distribution that are forced to the fish distribution. We then run the model from initial condition, which is homogeneous in the water column. So all state variables, except fishes, of course, are homogeneous, distributed over the water column. Then we run it for a certain amount of days until we approach the steady state. So these depth profiles of all the state variables are the steady state depth distributions under these constant forcing. Okay. Then we made a baseline simulation, which actually is constrained by the observations from the Red Sea. Such constraint meant by the observation involve what you can call calibration or tuning of some of the coefficients, which is not done automatically, but by intuition, you can say, actually say. So, because there is a large number of coefficients in such models, and there is actually no real challenge to fit it to observations. If you, tune all kind of coefficients. So we have not aimed for an optimal fit, but we have established a simulation which reflect the observations quite well. So that here the blue is the model and the red is the observations in these different panels. Also, the gravitational flux has been measured in the Red Sea in a study by Torstein et al. It's actually going for Akaba. And one of the calibrations are about tuning in the primary production that accords with observations, and also a gravitational flux that accords with observation, as we see here. Okay. Okay, some of the results, and this is perhaps what I call, actually what I call the non-surprising results. A previous suggestion in some previous papers is that the mesopelagic fishes in the Red Sea fuel a hotspot of heterotrophic activity in the mesopelagic, and this is supported by the simulation. We can see it from these are the simulated fish processes. So it's the fish ingestion, that's the blue line here. So they eat mostly in the surface water because there where most of the mesopelagic is actually produced. But it's also eat further down in the water column, but not much. Here we have the fish excretion and respiration and the fish defecation and mortality. So this is the loss terms. And you see down in the daytime depth of the fishes, there is a high loss rate. This line here is the total community respiration. So here is amount, these losses around 40% of the total community respiration. So it's quite high fraction of the total community reservation. In this panel, we have the vertical carbon flux, which has been divided into the gravitational POC flux, but also the net diffusive POC flux and the net diffusive DOC flux, and the net active flux, which is by migration, and also the total flux here. We are going to look at that kind of plot also later. So what we find here is that the fish in this basic run or simulation of the Red Sea contributes to about from 20 to 30% of the total donor flux between 200 and 400 meters. And it's increases the role of the active flux increases with depth until the migration ceases, of course. But then there is an important point here, and that is that the fish defecation and mortality, which occurs all over the water column in the model, also fuel the gravitational flux deep into the mesopelagic. And this fueling of the gravitational flux below deeper than 200 meters is seen as reduced attenuation, which means increased depth penetration of the gravitational flux. So the fishes also, of course, influences the gravitational flux, also within the mesopelagic. And this is quite relevant for the interpretation of Martin curves and also trap measurements. Here we can see the trap measurements in the Red Sea. And the observation actually can, well, the attenuation of this curve, the observation is the red points here. The attenuation is quite low, and actually it appears negative from this step to this step, and this is for several of the measurements there, which can be explained by fueling from the mesopelagic fishes into the gravitational flux. And that could be something that we should look for also elsewhere in the ocean, that actually the Martin curves and the attenuation are reflected by the fishes and what they leave in terms of mortality and defecation within the mesopelagic. Okay, the surprising result. When we start to manipulate different, particularly the forcings of the model, and the forcing of the model is here fish mortality, because that's the closure of the model. When you go up the food chain, the fish is at the top, and of course we have to close the fish with something that is called here mortality. We cannot model the mortality since we have no predators on the mesopelagic fishes. And of course, all such ecosystem models will have a closure problem at the end, because there will also always be a top predator, which you have to specify the mortality in somehow. And what we see here is that when we change the mortality of these fishes, which in the baseline, it's actually based on measurements of mortality, but those are quite uncertain. We see that the euphotic depth changes a lot, and also the relative composition between the diffusive and the gravitational fluxes. The active flux doesn't change much. And you can see it here that when we put the mortality at half of the baseline, the euphotic depth is around 130 meters. When we double the fish mortality, it is much shallower, something like about 30 meters or something. And also the flux composition is very different. I will show that in the next slide. So this is the half fish mortality here, and we had the double fish mortality, and we had the baseline simulation here. So when they change the fish mortality, the net primary production is more or less the same. It's changed a little. The euphotic depth changes from 136 meters here to 32 meters here. Also, the total sea export changes about 30% from this run to the double fish mortality. Double fish mortality means low fish abundance, and low fish mortality means high fish abundance. So that's another way to state it. The active transport by deal vertical migration is more or less the same. It's not that different, and that's might appear surprising, given that the fish abundance is much higher here than here. But the most surprising, as I said, is this change in euphotic depth. Just to say something about also the turbulent diffusivity or the mixing, because the mixing or the water column is what brings new nutrients into the euphotic zone. And that's the first order process to determine both the NPP. If you double the mixing, you more or less double the NPP. The euphotic depth is not as sensitive to these changes than to these mortality changes. And also the total export and the active export reflect the diffusivity or the nutrient input to the model. So this is not surprising at all. But I include it just to show that the euphotic depth is much more regulated by the fish mortality than the euphotic depth in this model. I don't say this is the case in the nature. I'll come back to that. Okay, so the fish-induced food web cascades have pronounced effects on water column structure. That's the main point here. I'm not going to explain this. This shows the food web composition for different scenarios of this fish mortality along this axis and for the turbulent diffusivity along this axis. I will just point at this simulation with half fish mortality and this with high fish mortality, double mortality. And those are also plotted here, and we will have a closer look at that figure. Because the low fish mortality is actually high fish abundance. And if you look at the diatoms, so now we turn into the diatoms, we see then when there is a low fish abundance, the diatoms disappear from the model. At high fish abundance, there are lots of diatoms that are actually dominating the autotrophic biomass. And you also see there is a shift in all state variables according to this mortality. So what's happened is that we increase the mortality of fish, then we decrease the fish abundance, which means that we increase the mesozooplankton, and then we decrease the diatoms, because mesozooplankton graze on the diatoms, and also decrease the ciliates. And then we increase this group, decrease, increase. So if you look at the DOC, for example, it looks more like in the tropical systems, while in the other system, it's, well, in the high fish abundance scenario, it's look more like this. So all these state variables changed a lot with the change in the mortality forcing. Also with the decreased mortality leads to more fish, less zooplankton, more diatoms. So this is not surprising, this cascade. The surprising thing is the consequences for the depth distributions, and particularly for the euphotic zone. And let's have a closer look at this. And here is the diatom nutrient trap, which we propose as a hypothesis, which emerges from this simulation. It's emergent property from the model in a way. So the diatom growth characteristics in this model, which are actually based on observations and experimental work, make the diatoms grow at the bottom of the euphotic zone. Here the diatoms trap upward silicates because they establish at the bottom the new silicate and the new dissolved organic phosphorus diffuse all the time up here, but are taken care of by the diatoms primarily, which then stops nutrients to diffuse further up into the upper part of the euphotic zone. So this makes the diatom nutrient trap down here a very oligotrophic upper euphotic zone with DIP or dissolved inorganic phosphorus, as well as silicate depletion, which we see here. Increased grazing from mesozooplankton, like in this red, all the red curves are here, weakens the diatom nutrient trap. Actually, here it's totally disappeared in this run, where when the mortality of the fish is not very high, it's double of the baseline. Then actually the model, the diatoms disappear in the model. And the euphotic depth becomes much shallower, simply because there are no trapping of the nutrients by the diatoms, and then there becomes more both regenerated and new nutrients up in the upper part of the euphotic zone. Okay, so this is well, the hypothesis that emerges from this study, and which was the surprising part. So I end with this, but before ending, just some remarks about the closure term and model uncertainty, because this closure terms, which very often are hidden in modeling studies, and that's unfortunate actually, because small changes in this model closure, which is fish mortality in our model, might actually cause severe changes in simulated scenarios, as we have seen in the presentation here, and actually destroy any resemblance with observation used for that we have used for the model calibration. And also this is not new, is also a warning in this paper about this closure problem. But playing with these closure terms, as we have did here, but also with other model properties, might provide a new hypothesis and insights. And we hope or suggest that this diatom nutrient trap might be such a new insight, but of course we need observational studies to actually see if this is a model property, just a model property, or actually is a natural phenomenon. There are some studies that support that this is actually a natural phenomenon. We have written about that in the paper, but I will not elaborate on this now. Okay, thank you.
Excellent. Thank you very much, Dag. Yeah, very interesting. So let's see once again if people have questions or comments that they want to come in with. So while people are thinking, a question from me, I'm trying to remember the schematic that you have from the model. Do you have a feedback from the fish on the microbial system, in the sense of, you know, their excretory products, fecal pellets? Does that get recycled within?
Yeah, everything is recycled. Yeah, there is mass balance. So nothing disappear except we have not mass balance of the carbon that is lost in respiration, if you see what I mean. That is lost from the model domain. Yeah.
So that means that the schematics you were showing in terms of when you change the mortality on fish, then you have less fish, you have more zooplankton. In addition to that sort of chain of consequences, there is a feedback on the system as well, and it's just that those direct links seem to be having a greater influence. Is that right?
Yeah, there are feedbacks because of the losses, of course, because all the losses are ending up as nutrients, and then or CO2. Yeah, so everything is taken care of. There is nothing lost out of the model domain.
I was just trying to think through that if you reduce the amount of fish, so one thing is that the amount of your
Well, I actually not reduce it. I increase the mortality,
so
and the mortality also ends up as
oh right, so
reduced. Yeah.
so it's not just a predation pressure is reduced on zooplankton and they grow. You're also changing the flux of nutrients or the turnover of nutrients into the rest of the system.
Well, when the mortality on the fish increases, there becomes less fishes, and the actual loss from the fishes might be more or less the same.
Right.
Yeah, but that is quite complicated. But this is a closed system in a way. Yeah. Yeah.
Thank you. Has anybody got any comments or questions? Here we are. So Claire, do you want to ask a question?
Hello, sorry, just in case I missed that there. I was just wondering when I think you were talking about mesopelagic community respiration.
Yes.
And I was wondering how did you account for the fish as part of that respiration, or how did you extract that from there? Was that also forced, or was that like from the model itself? For the fish respiration?
That's from the model itself. It's not forced. The fish respiration, you mean? That's model. Yeah, yeah. That's dynamic.
Okay, so how did you like measure that, or how did you account for it?
No, well, by respiration rates.
Okay, so just from like fish respiration rates in general.
Yeah, and defecation rates. But of course, this is connected to the feeding.
Okay,
yeah.
Is that for those particular species of fish, or does?
Well, we have tried to use the mesopelagic, the bentosema kind of fish. Yeah.
Okay, got you.
Yeah. Well, it's described in the paper, but because there are lots of processes here that I cannot go into. Yeah, yeah. Actually, too many.
Yeah, it's a lot. Thank you.
Excellent, thank you. So I can see we're right up against the hour. So unless there's a quick question that anybody would like to ask, then Helena, did you want to come in quickly?
Hi, thanks. That was really great, Doug. I really enjoyed that. Thank you for explaining more about your paper. I'm curious to know, you may have mentioned this, where you assume mortality occurred and how would that affect carbon flux, depending on whether that mortality is occurring mostly above or mostly below the flux boundary. And I'm curious to know a little more about that, given that you found that the mortality, half or double didn't make a huge difference in fish carbon flux.
No, the fish carbon flux is more or less the same. And the reason for that is when you increase the fish biomass, you decrease the zooplankton. So the net feeding is more or less the same. It is actually the production that drives how much flux is going through the food web. Yeah, because this is a kind of steady state. If you increase the fish biomass, you must do that on the expense of the mesozooplankton. And then you get less efficient feeding on the zooplankton because it's simply less, yes.
Okay.
And the mortality is forced not at particular depths. It's the same kind of mortality rate we apply over the entire water column. So we don't apply the mortality either up at large depth and shallow and that kind, but the same rate all over. Also, we don't make any assumption on where the fish is feeding. They are feeding where there are food.
Mm-hmm. Okay, thank you.
Yeah.
Mm-hmm.
Excellent, thank you very much. So we've slightly crashed the hour. So I'd just like to say a big thank you to Dag and also to Federico, our previous speaker. We will put the talks up on YouTube soon. I'll also make sure to add the papers related to the talk so people can look at the details in a bit more detail. The next talk, I should warn you, is coming up soon. So the December talk is only just over a week away. So please do take a look at the webpage for that. Otherwise, thank you all very much and hopefully see you on future calls.